So we made an announcement in early September about a new capability that we call LightSpeed. And LightSpeed for us is basically the work that we've been doing with NVIDIA in particular to essentially remove the bottlenecks that have conventionally been imposed by legacy NAS systems in the service of next generation AI applications. And so to explain the problem, what you have in the storage space today is basically you have two options. One is you can go down the path of buying a parallel file system, an HPC storage technology that is proven for RDMA and is deployed at some of the most sophisticated research environments in the world. Or you can go down the path of a NAS. NAS is obviously very easy to deploy, but the primary problem with NAS today is that you get about 2 gigabytes a second of a single stream of TCP performance per every NFS mount point. And so if you think about some of these next generation AI computers, and we're working with a lot of the different manufacturers of systems in the AI space, the expectation is far beyond 2 gigabytes a second in terms of single machine performance. And I can give an example in a moment. But the second consideration, I actually had dinner with one of the largest AI practitioners in the world last night, and they're talking about buying mountains upon mountains of AI processors. And the second consideration with all of this is if you're going to start to cluster all these systems, then conventional NAS also doesn't work because the scalability simply isn't there. But on the flip side, if the alternative is to use some exotic HPC storage technology, and I've been familiar and associated with many of them throughout my years, the challenge becomes how do you democratize AI across all of the different types of enterprise customers in the market? Because not every customer has 5 PhDs to manage an HPC parallel file system. And then the final challenge is, of course, that storage tiering doesn't work. And so there are vendors out in the space that are trying to save money because these applications, they demand an average TensorFlow request that we see with our customers today. Even though the data sizes, the file sizes may be in the gigabytes or even larger range, those files are basically packed with a bunch of images that are getting requested and read from the range of a few hundred kilobytes or even in certain cases a few kilobytes. And so you can't implement these codes against infrastructure that is hard drive based because there's simply not enough IOPS there to feed an AI processor. But you have companies out in the market that are implementing tiered storage solutions that either go down to some internally tiered storage or they're going out to some S3 storage system. And here, when an application has a cache miss, the performance can fall off a cliff by a factor of 50x. So the general conclusion from both the Department of Energy, which issued a many 100-page AI for Science report a few months ago, as well as Gartner, is you need low-cost, very large pools of flash for this, and that's basically why we founded the company. And so what I'm here to talk about today is the fact that you can use NFS to get the world's best performance from an AI perspective using some enhancements that we've pulled from the NFS kernel. Okay, so the goals are simple. One is we wanted to enable a platform that can give you all the performance that you can get from a single machine, has multiple ports, and drive I/O to a single mount point. If you look at the reference architecture documents from a lot of the AI reference architectures that come from different NAS providers, what you'll oftentimes see is that they'll recommend, in order to get beyond 2 gigabytes a second, that limit that I said earlier, which is a TCP limit, just do things like have multiple mount points. And basically that puts the problem at the foot of the user or the practitioner, because now you have multiple different, essentially, drives within that system that a user has to arbitrate in order to get an performance. So we said, that's not going to work. You need a single mount point. And we wanted to stick entirely to the NFS RFC so that customers don't have any complexity. And so how we do it is we've enabled a way to use all of the network interfaces. We figured out a way to distribute the load across these interfaces in a very balanced way. We added support for port failover that we contributed upstream. And then finally, we're using RDMA that we've supported for the past, 2 years now. And so in addition to the RDMA capabilities, which first and foremost take you from 2 gigabytes a second to being able to saturate the connection of any kind of NIC that you put within an AI computer. So let's say 100 gigabits, you're looking for 10 gigabytes a second. That's what a single NIC can do. there's a new capability in the NFS kernel called NConnect. And that basically adds multipath by opening up multiple simultaneous connections for a single mount point. So not only does RDMA solve the TCP limit where you're core limited in terms of handling client IO processing, but NConnect comes in and it enables many more connections from a single machine across a single mount point so that you can actually feed all of these very high performance AI processors.
Hey, Jeff,
so this multipath.
I do have a question for you, if you don't mind. So is that an effort to make the VAST cluster look like one, as opposed to have multiple VAST clusters where you kind of control performance for the individual components? You know, more going from a centralized architecture more to a distributed architecture, for example.
With NConnect?
Yes.
So NConnect still, the client expects to see a coherent namespace. NConnect can't take like 5 individual file servers and glue that into one parallel presentation of data. It doesn't have the smarts to handle the namespace management. What it's doing, actually I have a slide for it in just a second, is you basically set up a number of local ports on a host, and you can say, okay, I can talk through, you know, ports X through Y, and then you get also a collection of remote ports on the server side, on the storage side. And so those two both need to be more than one in order to do an NConnect operation. But on the storage side, it still has to be one coherent global namespace. So storage has to manage that. Does that answer your question, Frederick?
Yes, it did. Thank you.
Sure.
Hey, Jeff,
so
this is Ray. So you mentioned GDS earlier. Does the solution support GDS protocols and stuff?
It does.
Over NFS?
You betcha.
Yeah, GDS supports NFS over RDMA, and then the multipath is the step above that.
Yeah. Okay.
Well, we're the only folks they support it with at the moment.
I see. Okay, that's important.
So and you need GDS for the simple reason that if you look at this picture right here, what you have are 8 200 gigabit ports coming out of an NVIDIA machine. If you had to funnel that IO through the CPU memory, then you would basically be limited to what you could drive at around a maximum of 4 ports. And so there's inherent performance bottlenecks in the system that come from how they do PCI switching into main memory that you have to work around in order to see the full capability of, for example, in this case, a DGX A100. Even though AMD ROM systems are super fast and they have great memory bandwidth, an NVIDIA system is built with even more network connections that overwhelm even the fastest, some of the fastest CPUs.
So
anyway,
Jeff, I have a question about this. So can you talk to how people are actually using this technology? Because you made a comment in one of the earlier slides that it's too complicated for enterprise IT. So I'm just trying to understand, like, how are people actually using it? Not the potential, not the theoretical. I mean, how are folks actually using this today?
how are they using our storage? How are they using GDS? What in particular you're talking
well,
about?
Okay, so you're talking about, let me back up for a second. So sure. I'm just trying to understand why is this solution relevant and how does it kind of fit in, and how people are using it. And so if I understand how people are using this solution, like what you have on this slide, then maybe I can have an appreciation to understand the context of it, because I'm really having a hard time following along.
So our customers are using these systems predominantly for training and to some degree inference. And we have a wide cross-section of customers in research environments where customers have had comfort and familiarity with things like parallel file systems. But those systems have a rather extreme cost when it comes to deploying flash. Or we have enterprise customers that don't have that same level of comfort with some of those sophisticated storage systems. And we come in and say, you can simply use the clients that you have within your operating system. You can get all of the performance that you're looking for or that your applications demand from these next generation AI systems. And the flash is, of course, again, still much more affordable than competitive flash offerings. So that makes it possible to build extremely large training and inference corpuses that take away the considerations that customers have previously had around where do I store my data and how much is it going to cost me to store this in flash, and should I look at some sort of tiered solution. So If you put that together, it's a very large scalable pool of all flash that's for the first time very affordable, that takes away the performance limitations that have basically kept customers that are at the bleeding edge of some of these new AI systems from using NFS.
That's super helpful in the sense that before, when I looked at my data lakes and other sources of pool, I've always put some type of shim in between the storage and that in my AI engines, because the underlying storage just wasn't fast enough. So what types of use cases has this enabled some of your customers?
So we have a very, very broad cross-section of different types of AI use cases. I would say that the ones that demand this level of what's called GDS performance, we see two primary applications. The first is computer vision. If you're using this for anything from, let's say, an autonomous driving project to, we have a lot of bioinformatics environments that are using this for reading through electron microscope data. We have intelligence customers that are using computer vision to do things like read through satellite images. And then we have, actually there's a case study at the end of this with an organization called the Martino Center that uses the system to go and read medical images so that you can accelerate the time to patient care. And here, the commonality across computer vision is very, very large data sets that when you train on them result in extremely large bandwidth problems, not just for a global storage cluster, but the whole concept around accelerated computing and GPUs and AI processors is we can shave down 100 systems down into one. Well, that compute concentration equally creates an IO density that conventional NAS systems were never designed to solve for.
So Jeff, if I'm kind of playing that out a bit, I think I'm getting it. Essentially, what you're presenting is a storage solution, and when you talk, I'm still kind of going to that question that I had around the AI piece. It's not that there's AI within the technology that you're presenting as much as this is a solution that might be purpose-built for AI types of workloads to be able to operate. Because those are two different things, right?
Oh, for sure, for sure. To be clear, we're building a storage system. And what we did when we started is our conclusion that AI workloads will ultimately be applied across all data sets. And so the first objective of the company is to modernize data without incurring a lot more cost by making it affordable now to use flash for all of your data set. And the early days of AI, what you have are specific projects that are emerging. But we also have, for example, media customers that are taking the last 20 to 30 years of their content and running AI processes against assets that they didn't even know the term artificial intelligence for when they originally captured it, for reasons of enhancing their advertising services or things like this. And so what we're not expecting is that there will be this cottage industry of applications that are running on bespoke storage, driving AI adoption. We think the opposite. AI will just become woven into everything that we do. And that means that you need to modernize all of the data.
Okay, so saying that then, why would I go down this path and build it all out locally as opposed to just leveraging a cloud type of approach that is specialty built for those AI workloads?
So I think, Tim, my follow-on question to that or example will help kind of color.
Yeah, go for it.
A bit. So I worked in a pharmaceutical for drug discovery and collecting massive amounts of genomics data at the edge. That data is extremely difficult to move to a centralized cloud provider. So something like this is something that my users begged for. Like, Keith, can you just give me the capability to process the data at the NAS where we collect the data versus you asking me to shuttle a petabyte of data to the public cloud or to some adjacent specialty cloud provider? It's basically giving me that general purpose compute I need to run AI at the edge is one of the use cases I would use this for.
I agree.
Yeah, so
now, is the edge now everybody's data center, Keith?
It's pretty much.
Yeah.
The problem with the public clouds is not to get the bandwidth, it's the latency. It's extremely difficult to get low latency and certainly consistent latency, which is extremely important for GPUs. CPUs, they're not that sensitive. But if you have like a couple of $1 million worth of GPUs and you're trying to mimic something in the public cloud where you have semi-control over something you have on premises, it's unbeatable, right? And anybody you talk to from an AI perspective will tell you that keeping the GPUs busy is the #1 thing to take care of.
These machines cost hundreds of thousands of dollars. And more importantly, when you deploy them in a cloud service, the multiplier goes up exponentially. And so as Frederick mentioned, keeping them busy is the #1 objective, and IO is very often the #1 path to keeping these systems busy. Now, Tim, to your question, what we see is a line of demarcation around critical mass, right? And organizations like Intel and like NVIDIA, they sell on-premises systems for a reason, which is once you get to a certain point where you can efficiently start to scale up your organization to build these clusters, the savings that you can realize versus deploy this in a public cloud is monumental. You're talking in terms of tens to certain times hundreds of millions of dollars of difference. So we've seen with some of our customers that are now implementing some of the largest AI projects in the world that a lot of those efforts did start in the public cloud for reasons that you could get ephemeral access to compute resources on demand. So it made for a great place to implement proving grounds. But once you start to operationalize this infrastructure and it's running at high utilization, then the accountants will all tell you that it has to be brought back down on-prem because the cost points are just completely prohibitive. And I'll put a very fine point on that. Here, what you're looking at is a solution today that costs, somewhere in the order of a 2-to-1 data reduction, about 30 cents per gigabyte to capitalize. Now, if you compare that to what you can do in the cloud today, an all-flash file system in the cloud will cost you 30 cents a gigabyte per month. And so over a 5-year period, you're talking about a 60x delta in the cost of infrastructure. On top of that, when we started VAST, we didn't identify that we could only win this war on a cost basis. You had to deliver capability. And so by solving the price performance paradigm, we feel that it's very competitive to what you could otherwise find within the public cloud.
Hey, Jeff, I'm still trying to figure out regarding this. So are your customers storing their data lakes into this VAST storage, or are they storing more like structured data there, or both?
It's a distributed file and object storage system, so it's all unstructured data. You could think of as a data lake. Some people just call it their scale-out file system environment. But it is not block storage for example, databases. Now that said, people also can implement scale out, and in certain cases, even AI processor enabled databases on file systems, right? So internally to, for example, this machine that we're showing here, there's a set of IO libraries that can basically abstract any file system. So people use file systems for things like graph databases that are accelerated by modern processors and things like that. But the objective is to not have a bunch of different systems on the floor for specific fit and purpose, Katie. So, for example, that's a notion that we think is kind of footed in how legacy storage has been deployed. What we're building is a system here that you can use for almost every application. You can use it for VMware, you could use it for WordPress, you could use it for Microsoft applications. You can equally use it for next generation AI processing.
Hey, Jeff, the GDS protocol, as far as I could tell, was, it went directly from storage to GPU memory. It seems to imply, so, I mean, behind these VAST controllers are the actual storage devices themselves, the Optane SSD enclosures, I guess you call them. And then up GPU memory is, what's the sort of bandwidth between those two that you can attain with the GDS solution over NFS, over RDMA?
Sure. I'm glad you asked, Ray. So Yeah, we've been working on this. So GDS essentially routes all of the I/O that goes into a GPU high bandwidth memory device through this. I should say, classic I/O routes that through CPU memory and CPUs, which become a bottleneck versus the I/O capability of GPUs. Now, what we've done is threefold, and this is the other kind of primary announcement around LightSpeed. Is what we've combined is RDMA that allows us to DMA directly into the machine at the destination of the machine's choosing, and we'll talk about destination in a moment. Multipathing, which means you can create an NFS mount point that goes across multiple connections. Those multiple connections can now be implemented across multiple ports within a machine. And an A100 has 8 200 gigabit ports, just to put things into perspective. And the other thing that we had to contribute was NUMA awareness, which is, you've got multiple switches within these machines, and if you run I/O through the machine in the wrong way, you can kind of lose a little bit of performance benefit. So we handle the non-uniform memory architecture such that we get really, really clean lines of communication into the GPUs, and then we layer on GPU direct storage. And so the question is, what can you do with a single client? We show 3 different performance outcomes here. The first, and all of them, by the way, are done with our system. So we're not even comparing with other file system technologies that are out in the market. So we set up different mount points for an application, right? And we take an A100 and we say, okay, what if you just did a standard everyday TCP NFS request from a GPU down into storage? And here you can see 2 gigabytes a second of performance. That requires about 1% of the system CPU cores to implement, and you're basically limited to the capability of just 1 core. Now, the second thing we did is we layered on RDMA and multipath. The I/O is still, in this case, going through the CPU memory and the CPUs of this AI processing system. And so at this point, 50% of the performance is dedicated to handling what I would call storage traffic. And the remaining 50%, which actually isn't seen here, is taking that data that's in the CPU memory and then shuttling it off to the GPUs. And here we can see just around 46 gigabytes a second of performance, which is monumentally faster than what any customer has ever expected to get from NFS. But that's not where it stops. So then you do CPU bypass by implementing GPU direct. And basically there's a set of primitives in the NFS client code that ships in this case that says, okay, instead of doing an I/O where you DMA a piece of data into the CPU's memory, instead put that in this destination, which is the GPU memory. And so now your data doesn't have to go through the CPU at all. It doesn't have to go through the CPU memory. And here we've seen 162 base 2 gigabytes a second, or 174 base 10 gigabytes a second, which is, in the order of around 90 times faster than conventional NAS.
And this is just moving data into the GPU memory. It's not actually doing anything at the GPU to process, train, or anything like that. This is kind of just an iometer kind of thing with the GPU memory. Is that what we're showing here?
Yeah, basically.
This is a modified version of FIO that NVIDIA uses called GDSIO.
Right.
So the modifications are basically to set the mount point such that there's a different destination in this case, which is the GPU memory.
And this could be read or write, or is this just reading from VAST?
Well, the workloads are predominantly random read in nature when you're dealing with AI. So that's where we spend all our time on. You could write at this rate of speed if you wanted to, although we typically see when we get into our AI customer environments that no more than 3 to 4% of the network traffic or the storage traffic is writes. It's almost all reads.
Will you be supporting any of the other vendors that are coming out with GPUs?
Yes. So we already have customers using other ones. That said, that there are specific optimizations that have been made here for NVIDIA for reasons that they have a system that can make use of it. But that's the nice part about NFS is that it's completely transversal. And NFS over RDMA and NConnect are already in the kernel. So all of this, NFS with RDMA and multipath can work on any x86 machine today, and
So
makes it fast.
just a follow-up question, and looked on the website. I know I've talked to Howard about this before, but I don't remember. So do you work with virtual machines as well?
We do. We have a number of customers that run VMware on our system today. We also have a CSI for containerized environments, so we work with Kubernetes as well.
And NFS with GPU Direct is something that's just come out. Is it released in NFS version 3 or version 4? Or
So NVIDIA has not yet formally released GPU Direct storage. This is all beta.
This is beta.
So
their intention
the
is
whole concept of GPU Direct storage, both for parallel file systems and for NFS, is beta.
Yeah, but they've released GDS for Black, right?
Beta.
Even Black?
Anything GD with an S at the end is all beta until the end of this year.
Yeah, GDS as a concept is beta.
Okay.
But it's all about RDMA. So it's parallel file systems that support RDMA or NFS over RDMA, because the RNIC has to do the transfer directly into GPU memory.
Bingo.
All right, thanks.
So this, as best as we've seen, is pretty much the best performance that you can get. Like, you're nearly saturating 8200 gig ports here. And there's not anything in the market that's delivered more. And the nice thing about that is if you look at the kind of the competitive marketing of the other parallel file system vendors, they say you can't get there with NFS. And that's true if you look at the legacy approach to NFS. But what we've done is completely remove the bottlenecks so that you can do AI processing without having to implement very complex file system technology.
This is one VAS box or 20 VAS controllers? Yeah.
You can see the configuration at the bottom. There's 5 enclosures, and we have these file servers packed 4 into 2U that we call C boxes, compute boxes. So there's essentially, you're talking about 20 file servers and 5 enclosures to achieve this number.
I gotcha.
So we're just in the process of publishing the first very high bandwidth reference architectures with NVIDIA right now. And yeah, there's more to come on that topic. Okay. So the question earlier, I think that Tim raised, is who's using this? And an example of that is an organization that is a cooperation between MIT, Harvard, and Mass Gen called the Martino Center. And basically what the Martino Center has is some of the world's most sophisticated MRI and CT machines in their lab. And they only do research around biomedical imaging for, kind of in partnership with a lot of the large instrument providers. And as compared to like what you would find with, let's say, a Siemens imager when you go to the hospital to get your own CT scan, they're able to pull a very sophisticated raw data set that comes directly from the machine before it gets processed as it typically does in a clinical environment. And so with this raw data, what they're doing is they're now implementing AI against that in order for the purposes of basically seeing if there's more insights and more information that they can glean from this information if they have very, very powerful systems to process on them. So this was actually the first LightSpeed deployment that we did. And here, when they started shopping for storage, their alternative was a parallel file system that was hybrid based, flash and hard drives. And as I mentioned earlier, that puts the burden of data management and performance management at their feet for reasons that, you can never do an effective, let's say TensorFlow request of 100 kilobytes down to hard drives. So then their researchers would have to start worrying about what the size of their flash cache is and things like this. Anyway, we came in at 25% less in terms of cost than the hybrid approach to hard drives and flash, which gives them a completely consistent performance across their whole training corpus. And that de-risks their GPU initiatives. And basically they took that money and allowed them to buy more processors. Yeah. So, but the bigger thing is, when we started, it's not just that we're religious about standard protocols for reasons that we want to make it easier from an operational perspective, but rather, if you look at the amount of data that is, being managed by most customers today, most of that data is not being generated by, for example, computer vision applications. It's being generated by legacy applications that for 20 to 30 years have been writing across standard protocols such as NFS or CIFS, now known as SMB. And then increasingly, a lot of these applications are moving to S3. And one of the reasons that a lot of the principals in the AI industry like our product is that it's eliminating that need to jump to parallel file systems, but also providing a bridge that avoids a challenge that is creeping into large organizations called shadow AI, where once a research arm starts to figure out what to do with AI infrastructure, they go and they turn to the enterprise IT team and say, hey, can you guys operationalize this? Well, if these are technologies that they haven't seen or deployed or have no other use for, that becomes a really tough value proposition. In our case, we've invented this system that's called universal storage for a simple reason that we want a single platform that you can use for all of your data. And what that allows for is if you've got these legacy data sets sitting on our system, now you can start to run AI applications on them without having to refactor anything or doing anything like that. And you get the best possible performance while you're doing so. And so we think this concept of universal storage modernizes data and makes it possible to start to implement Spark and TensorFlow and PyTorch and Caffe and a number of these different kind of Magnum-oriented applications without having to become HPC storage technologists.
So as an Intel provider or Intel partner, rather, where does the Intel Optane play a key role in this whole structure?
Sure. So the whole architecture isn't possible without Optane technology. And we use more than Optanes from Intel. We use x86 technology to drive the file system logic. We use
QLC flash.
A lot of their QLC flash. Thanks, Howard. And so if you look at it, what our logic sees is you've got all these containers that see a sea of Intel Optane drives and a sea of even much larger QLC flash infrastructure. And so Intel Optane for us basically provides a level of persistence that's similar to flash. And so we can think about it as a big distributed write buffer without having to worry about volatility challenges. It comes in at a cost point that is much lower than DRAM. And so that allows us to build much larger write buffers than what would have otherwise been affordable if we had to use DRAM. And if you combine these two, coupled with extremely low latency, you get something interesting. One is the writes get issued down to Optane in real time. The applications get an acknowledgement back, but the system isn't compelled to move that data down to flash immediately because the write buffer is so large. Now, the second consideration is that we don't have to have we don't have to have metadata resident per every one of our controllers that's in a container for reasons that each of the containers has access to this global shared pool of Optane technology. And at around 10 microseconds of latency, those Optane devices are pretty much faster than if you had flash drives resident to every controller. And so because of that, we've got a global metadata store where there's just one protected copy of metadata across the whole cluster, and we're not replicating that across a number of different machines. And as we look to scale, what we didn't want is to have a bunch of different machines all talking to each other at the same time, because that basically slows down the cluster as you start to grow it geometrically. And so because of Optane and because of NVMe over fabrics, this metadata can all just be kept on the other side of the network in the form of a compression dictionary, in the form of your directory structures and things like that, where no two machines have to talk to each other at all. And so one of the common knocks around scale out storage is that you have this law of diminishing returns as you start to scale out clusters. That becomes really problematic when customers start to think about deploying 100 or 1,000 or even 10,000 AI processors. Some of the organizations we're working with are thinking extremely ambitiously. And so the only way to get there is to have a bunch of different containers that all don't talk to each other that you can scale linearly, which is possible because of Optane technology.